For those of you who missed today's lesson, we'll quickly go over the content that was about cyclic quadrilaterals and the circle theorem associated with it. A quadrilateral, as you know, is a four-sided polygon. So what is a cyclic quadrilateral? A cyclic quadrilateral is a quadrilateral whose four corners lie on the circumference of the circle, as you can see here. So these are the four corners of the quadrilateral. They lie on the circle. So if even one of the corners does not lie on the circle, then it is not a cyclic quadrilateral. The property of a cyclic quadrilateral is that the opposite angles add up to 180. They are supplementary. And the circle theorem states that opposite angles in a cyclic quadrilateral add up to 180, and we use this property to solve problems involving inscribed quadrilaterals in a circle. Now, there are two examples that I have put up here, okay? Because here, a common error that students make while solving cyclic quadrilateral problems is that they take the opposite angles to be equal, but that's not necessarily the case. This is a particular case, and why does this happen? This is because here, this is the diameter. So both of these angles lie in a semicircle and are hence 90 degrees each. Whereas these angles here, they are also opposite to each other, but they are not equal to each other because they're not angles in a semicircle. As you can see here, this one is 104, this is 76. The only rule is that they should add up to 180. That is it. Now here, since the other measurements are not given, what we can say about it is only that if we were to call this as x and call this as y, the only information that we can give out is that x plus y is 180 degrees. To make it further clear, just so that you're very clear about what a cyclic quadrilateral is and where you can apply the circle theorem for that, is that check that all four corners are on the circle. So this is cyclic, whereas this is not, because although the three corners are on the circle, the fourth one is not on the circle, it's at the center. For this to become cyclic, this point should have been here or anywhere else on the circumference. Currently, this one is not cyclic, and we cannot apply the rules of cyclic theorem to this quadrilateral. Now let's solve an example that involves a cyclic quadrilateral. So the first thing you do is identify the cyclic quadrilateral. Here are the four corners. They are on the circle, so we can apply the circle theorem for cyclic quadrilaterals. The first thing that we can see is that this and alpha here and the angle here, which is 63 degrees, are opposite angles, and hence they have to be supplementary by the circle theorem. That will give us 63 plus alpha equals to 180 degrees, as they are opposite angles in a cyclic quadrilateral. Always mention the reason behind any angle fact or any of the numerical facts that you're stating. Opposite angles in a cyclic quadrilateral add up to 180, or they are supplementary, which would give us alpha equals 180 minus 63, and that is 117. We're done with alpha. Now let's head over to solve for beta. What can we see here? Now here the opposite angles are not given. However, we can find the beta in this particular case because this happens to be the diameter. And we know another circle theorem which states that angle in a semicircle is a right angle, which means that this angle, which is the angle in the semicircle, is 90 degrees. Hence, we'll be able to find out beta. Considering this is 90 degree, which that leaves us with the fact that 63 plus beta would add up to 90 degrees. So 63 plus beta would be 90 degrees. We are using angle in a semicircle. And that would give us beta equals to 90 minus 63, which is 27 degrees. We have a similar and extra problem, which you can pause the video and try for yourself. This is exactly the same as the previous one. We just called y instead of alpha. So you can simply state that 63 plus y is 180, which would give us y as 180 minus 63, which is 117 degrees, same as the previous example. And the rule is opposite angles in a semicircle. Right? This is exactly what we did in the previous example, and you can practice that. Opposite angles in a cyclic quadrilateral. Please make sure that you always mention the reason. Okay. Same goes for the other one. It is the exact, it's the use of the same rule. 104 plus x equals to 180. So x is equal to 180 minus 104, which would give us x is equal to 76 degrees. And the rule is the same. Opposite angles in a cyclic quadrilateral, right? Now here we are given no specific numbers, but all the values are in terms of x, and we have to find each of the angles. To solve that, we'll again use the property of the cyclic theorem as we identify that this is a cyclic quadrilateral. So these are the opposite angles. These two are the opposite angles. Hence, they should be supplementary, which gives us 7x plus 3x equals to 180. 10x is equal to 180, x is equal to 18. And that would enable us to find out all the angles. We'll start 3x is 3 times 18, 5x is 5 times 18, and 7x is 7 times 18. So this is 54, this is 90, and this is 126. We found out 3 of them. You could either add all of them and subtract it from 360 because it's a quadrilateral, so the angle sum would be 360. But in this particular case, we see that this angle is 90 degrees, which means that this one has to be 90 degrees as they are opposite to each other and they are cyclic. That means they have to be supplementary, right? The rule that we used here is angles in a cyclic quadrilateral. This is a theorem we used over here. Now here is an extension of the same concept, but we are given an exterior angle. The angle is exterior to the cyclic quadrilateral, and the measure of the exterior angle is 79 degrees. We are asked then to find the interior angle here. So the first thing that we need to identify is that this is a straight line, right? Because it's the exterior angle. Hence, this angle here, let's identify this as y and this is x. Right? So these are the two opposite angles in the cyclic quadrilateral, whereas this x makes 180 degrees here with the exterior angle, right? Because it's on a straight line. So what we have is x plus 79 is equal to 180 degrees because they are angles on a straight line. which would give us x to be 180 minus 79, which would give us x to be 101 degrees. So this angle here is 101 degrees. Again, using the property of cyclic quadrilaterals, we can see that x plus y is also 180 degrees. That means 101 plus y is 180 degrees, which would give us then y equal to 180 minus 101, which is 79 degrees, right? We could have seen that even by observing that they would turn out to be the same. So here is 79 degrees, which is the same as the exterior angle, which comes, or which we can deduct, leaves us with an interesting fact, or a theorem which says that the exterior angle of a cyclic quadrilateral is equal to its opposite interior angle, and you can use this fact for problem solving. That is it for today.